After spending 4 years working with the AggieSat laboratory at Texas A&M, I've learned that getting a satellite into orbit is only half of the challenge. Once it actually reaches space, the satellite still needs to know which way it is pointing. Its solar panels may need to face the sun, its antennas may need to face the Earth, and other cameras and scientific instruments may need to face a specific target. And if those components are pointing in the wrong direction for whatever reason, the satellite may not be able to generate power, communicate, or complete its mission at all. A spacecraft's orientation is called its attitude, and today I'll explain how satellites determine and control their attitude. First, I'll explain why orientation matters, then I'll describe the sensors satellites use to determine where they are pointing, and finally, I will explain how they physically rotate and stabilize themselves. Before looking at the hardware, we first need to understand why orientation matters. In their textbook on spacecraft attitude control, aerospace engineers F. Landis Markley and John Crassidis explain that attitude determination identifies a spacecraft's current orientation. Attitude control then points it in the desired direction. Now, it should be noted that attitude is very different from orbital position. Two satellites could be in nearly the exact same location but pointing in completely different directions. One could have its antenna facing the Earth, while the other could have its antenna facing away from the Earth. And that difference could determine whether the satellite can communicate at all. Several other parts of spacecrafts also depend on proper orientation. Solar panels need enough sunlight to generate electrical power. Antennas may need to face a ground station. Meanwhile, a camera or scientific instrument may need to point towards the Earth, another spacecraft, or a distant object in deep space. NASA's Basics of Spaceflight explains that attitude control allows spacecraft to aim their antennas, point their instruments accurately, and control their exposure to sunlight and direct their thrusters. A satellite also does not need to remain pointed in one direction throughout its entire mission. For example, it might point an instrument towards the Earth to collect some information, then it may turn its antenna towards a ground station to transmit that information, and then later it may turn again to expose its solar panels to more sunlight. The Hubble Space Telescope shows just how precise this pointing has to be. According to NASA, Hubble can remain pointed at a target with no more than 0.007 arcseconds of deviation for an extended period. And NASA compares this to aiming a laser at the image of Franklin Roosevelt on a dime from 200 miles away and holding it there for 24 hours. That accuracy is necessary because Hubble observes objects that can be billions and billions of miles away, and even a tiny bit of movement could affect the clarity of the image. Before a satellite can point this accurately, it needs to determine where it currently is pointing. Satellites determine orientation by combining information from several different kinds of sensors. The first is a sun sensor, and as its name suggests, it measures the sun's position relative to the satellite's own position. And this can help the spacecraft find a safe orientation and keep its solar panels exposed to sunlight. Another sensor is a magnetometer, and a magnetometer measures the direction and strength of Earth's magnetic field. And it works sort of like an electronic compass. However, instead of pointing just north, it provides information about the magnetic field in 3 different dimensions. And for more precise orientation information, satellites can also use star trackers. In a NASA Attitude Control primer, engineers Andrew Nguyen and Andrew Zufall explain that star trackers take pictures of stars. The computer then compares the patterns in those pictures with an onboard star catalog. It's kind of similar to recognizing a constellation in the sky, but the difference is that the computer can examine many different kinds of star patterns and use their exact positions to calculate the satellite's orientation. Satellites also use gyroscopes, and unlike the other kinds of sensors, a gyroscope does not need an outside reference like the sun, Earth, or stars. And instead it measures how quickly the satellite itself is rotating and the direction that it's rotating in. Each of these sensors provide useful information, but each one also has its limitations. Small gyroscope errors, for example, can build up over time. A star tracker is very accurate, but something can temporarily block and interfere with its view. And a sun sensor provides a useful reference, but it's not as precise as a star tracker. And that is why satellites usually combine several different kinds of sensors instead of depending on one. NASA explains that Hubble uses sun sensors, magnetometers, gyroscopes, star trackers, and fine guidance sensors. Its computer combines all of these measurements and information to create a more dependable estimate of its attitude. Other satellites use the same general approach. According to the European Space Agency, ENVISAT uses Earth sensors, star trackers, sun sensors, and gyroscopes. Together, these sensors allow it to maintain its Earth pointing accuracy better than 0.03 degrees, and using multiple sensors improves both accuracy and reliability. So if one measurement is unavailable or inaccurate, the satellite still has other information it can use. But determining the satellite's attitude only tells the system whether it's pointing correctly. The next step is actually changing its orientation. Attitude control works through a continuous feedback loop. First, the sensors will estimate the satellite's current attitude, and then the flight computer will compare that estimated value with the attitude required by the mission requirements. And if the two don't match, the computer will command an actuator, which is a device that can physically rotate the spacecraft. The satellite will then continuously repeat this process: sense, compare, correct. One of the most common attitude control devices is called the reaction wheel. And the reaction wheel is an electronically powered wheel mounted inside the spacecraft. So when the wheel accelerates in one direction, conservation of angular momentum will cause the satellite to rotate in the opposite direction. You can imagine this like sitting in a chair that spins, and if you hold a spinning wheel and change its direction, the chair and your body will react by turning. And a satellite uses the same basic principles. Since reaction wheels operate inside the spacecraft, they can rotate it without consuming any propellant. And NASA reports on small spacecraft guidance, navigation, and control explains that at least 3 properly positioned reaction wheels are generally needed for this. And this allows the satellite to control its rotation around all 3 axes. Reaction wheels are also very precise, but they do have an important limitation. Small outside forces are always affecting satellites, and these can include atmospheric drag, gravity, and even pressure from sunlight. And as a reaction wheel continuously corrects those disturbances, it may have to spin faster and faster and faster, and eventually it can reach its maximum speed, and this is called saturation. Once a wheel is saturated, it cannot provide any more control in that direction until it slows down. To solve this problem, satellites can use magnetorquers or thrusters. A magnetorquer creates its own magnetic field inside the spacecraft, which interacts with Earth's magnetic field, and that interaction produces a rotational force. This force can rotate the satellite or allow the reaction wheel inside to slow down, so that the spacecraft can still maintain its orientation. Magnetorquers are especially useful on small satellites in low Earth orbit because they don't consume any propellant. But they do depend on the Earth's magnetic field, and they can't provide the same strong or immediate control as thrusters can, especially at a distance. Thrusters work by expelling propellant. This creates forces that can turn the spacecraft. They can perform much stronger maneuvers, but every maneuver uses the limited amount of propellant on the craft. And once that propellant is gone, well, the satellite can't be refueled for now. All of these sensors, computers, and actuators must function together, and because repairs are extremely difficult after launch, engineers test the complete system beforehand extensively. In a 2024 peer-reviewed study, Franklin Tikwana Kawakira and his colleagues tested a CubeSat attitude control system using a computer model, flight software, onboard processors, and physical hardware. And a CubeSat is essentially just a modular kind of satellite, like a cube. This type of testing allows for engineers to find inaccurate sensor readings, software errors, or actuator problems while the spacecraft is still on Earth and can be repaired. The Kepler Space Telescope shows the importance of these systems and how engineers can adapt while something fails. And according to aerospace engineer Kip Larson and his colleagues, Kepler actually lost 2 of its reaction wheels. So with only 2 reaction wheels, the telescope could no longer use its original method of 3-axis control, which then threatened to end the mission. Instead, engineers developed a new version of this mission called K2, and they used the remaining reaction wheels, small corrections from the thrusters, and even pressure from sunlight to balance and stabilize the telescope and achieve a new orientation. The sunlight had actually originally been a disturbance that the system needed to correct, but engineers were resourceful and found a way to make it part of the solution. Ultimately, a satellite must know where it's pointing and be able to change that direction when needed. Correct orientation allows it to generate power, communicate, and aim its instruments. Sun sensors, magnetometers, star trackers, and gyroscopes determine its attitude. Reaction wheels, magnetorquers, and thrusters then rotate and stabilize it. Space may have no ordinary up or down, but by repeatedly sensing, calculating, and correcting their orientations, satellites can find exactly the direction their missions require.